So what we're switching to today is actually a master's defense, and it'll be of Miguel Cândido, and who's actually only been with us for 2 years. It's quite unique, as you're going to find out. These are the naval officers who come to us, have a 24 to 25 month deadline, and every one of them produce in that time, which is something that's really quite remarkable. I'm very proud to have Miguel as a grad student. The committee are Brian, who's wandering the Camino Trail, Larry, Tom, and myself. And Miguel is a lieutenant in the Portuguese Navy. He went through their Naval Academy back in 2011, saw the light in 2017, and went to white ships, to hydrography. And he's part of a long line of hydrographic officers that we've known for over 20, 30 years. Larry will remember Fernando back at UMB. And it's really great to have these people who come in. They've all got CAT already. They all get it from their Naval Academy, their in-house training. And so they give an awful lot to the department as well. But in Miguel's case,
and say where Fernando is now.
I think it is in a NATO center, an excellent center for geographic intelligence.
Before that, was he the director of the training center?
Maybe some years ago. It wasn't from when I was.
So
there's 6 or 7. They all end up as admirals and go off to do Law of the Sea and other sort of stuff. Many of them in many other aspects of hydrography. But Miguel will be describing his thesis he's been doing over the last 24 months. And I think better to let him describe it. The title is there. And just tell you that the outline of this master's thesis, I tend to think of them as shorter. But the presentation is supposed to be up to 40 minutes. I don't think you're going to see that today, which is great. But no, I just think clarity and swiftness is always better. But what we're going to do then is we're going to go through the committee twice with a series of questions. I've got questions from Brian because he's not available. And then we'll open it up to the group here as well. So with that, Miguel, I'll hand it over to you.
Well, thank you for the introduction, John. Ladies and gentlemen, good afternoon, everyone. Welcome to my defense presentation. For the people watching over Zoom, especially if you are watching from Portugal, obrigado. Thank you for watching. And let's start with this. So the presentation that I'll be doing today, as you can read, it's about implementing a reference backscatter calibration technique on a multi-sector multibeam echosounder. So seafloor characterization, knowing not only where the seafloor is, but also what's the seafloor, and classifying according to one's needs. And conveniently, we are on the ocean decade as defined by the United Nations. And one of their goals is to provide us with a digital twin of the ocean. And for that, we need to know not only where the seafloor is, but what's the seafloor. On a national scope, there are initiatives such as the one encapsulated by the Presidential Memorandum of the United States about mapping the US EEZ, which not only states as an objective to map the seafloor, but also characterize it. And in the background, most of you might be recognizing this area. This is UNH's backyard. You can see Odeon Point. This is just seaward of the Piscataqua estuary. And if you wanted to characterize this area, of course, you could do some point sampling. You could collect some pictures, do some cores, some surface grabs, but that will prevent you, at least just by doing this, to get high resolution maps such as this one, which I think it was generated by Larry Ward's team, our own Larry Ward's. And this one classifies the seafloor regarding its superficial geology. And accounting that most national hydrographic offices already have high resolution campaigns for bathymetry, and they typically use multi-beam echosounders for that. Why not take advantage of another product, bottom backscatter strength, to perform this seafloor characterization? And bottom backscatter strength is basically the ratio of incident acoustic energy that gets scattered to the sonar by the seafloor, normalized by unit area. It depends on the insonification geometry, the used acoustic frequency, and thankfully on the seafloor physical properties. And if we sort it by grazing angle, we get what is commonly called as an angular response curve. And you can see several ARCs associated to different seafloor types. And you can already see that it can be a powerful discriminator of the seafloor type. But while it's very easy to distinguish, for example, between a rough rock seafloor type and a very fine silt, medium sands and very fine sands are only 2 dB apart on average. And for us to be able to distinguish that, our backscatter resolution must at least be that good. Unfortunately, what we get with our sonars is not the bottom backscatter strength. It's received acoustic intensities, which will depend on the sonar architecture, its source level, its receiver sensitivity, basically its beam pattern, on the interaction of the acoustic signal with the water column. It will suffer refraction, attenuation, spherical spreading, and finally on the bottom interaction, where the bottom backscatter strength is, and that's what we are after. But there are also other processes that will affect our signal. For example, the morphology of the seafloor will affect our insonified footprint. And so if we don't account for all of these processes correctly, we'll end up with bottom backscatter strength estimates that are not repeatable, even if we are using the same sonar, identical sonars, using the same frequencies. And so to avoid that, we have to properly reduce the backscatter. So that's what we are after, the bottom backscatter strength, and we think we can model fairly well the other processes, the bottom interaction and propagation processes. However, regarding our sonar, we are usually only have the beam pattern estimates that the manufacturers provide us with, and that might not be good enough to produce repeatable bottom backscatter strength estimates. And so in order to get absolutely referenced backscatter from our sonar, we have to calibrate it. And one of the approaches consists on using a reference target, such as these target spheres. And by swinging one of these targets over every beam of a multi-beam echosounder, we might be able to determine the combined transmit and receive beam pattern. Of course, a multi-beam nowadays has several hundreds of beams, and they are quite narrow, typically less than 2 degrees wide. And performing these operations, especially at sea, is not an easy task. Furthermore, the multi-beam has to be capable of splitting its beam in the fore-aft direction as well, and that's not a common feature of a multi-beam. This is an example for a Simrad ME70 that has that capability, but that's not what usually happens. And for conventional multi-beams, for example, Anzoni and Weber propose using an auxiliary sonar, a split beam echosounder, to help and fully position the reference target. Of course, now we have extra complications. We have to swing our target at the intersection of 2 beams, which gets even harder. And we also have to know very well the relative orientation and position of the 2 sonars. Of course, we can do this, apply the same process in a controlled environment, such as CCOM's engineering tank. And in this case, we can control really well the relative position between the target and the multi-beam. And so we can dismiss the usage of those auxiliary sonars. Of course, by removing the multi-beam from its natural habitat, the vessel, we might end up not working in the far field, in far field conditions, especially if we are using larger arrays with lower frequencies, because the tank might just not be big enough. Another calibration process uses the same type of facilities, but now instead of us having a reference target, we might replace it by a calibrated transducer. And so if we have a calibrated projector, we might be able to obtain the receive pattern of the multi-beam, and on the other end, by using a calibrated hydrophone, we can get the transmit pattern of the multi-beam. And the merit of this approach is that we can get these 2 separately. Finally, The last approach that I'll be talking about consists on using a reference area, basically a patch of the seafloor with homogeneous and isotropic bottom backscatter strength. And it goes like this. We use a calibrated sonar, popularly a split beam echosounder, because it can be easily calibrated using a reference target. And from it, we get a reference ARC. And then we can compare it with our uncalibrated ARC that we generate with the sonar that's not calibrated. And by comparing the two data sets, we might be able to calibrate the multibeam. In fact, Lefterakis et al. Implemented a reference area calibration approach. They used a single sector multibeam, a 2040, if I'm not wrong. But they assumed that the beam pattern of the multibeam was fixed in a vertical reference frame. So they didn't account for the motion of the sonar reference frame. And they used the single sector sonar. So they didn't also account for that feature. And what I intend to do is to build upon that previous work, but account for these extra complications. Which lead us to my roadmap, my calibration roadmap, let's call it like that. And before I go through each step, I would just like to remind you that this calibration technique is tailored for Kongsberg systems. And the set of correctors that I generate are only valid for a specific sonar operating at a specific mode. And by mode, I mean a combination of operational settings, such as the number of SWATs, the number of sectors, the pulse length, and the frequency of each sector. Furthermore, I'll be presenting results using EM710 and EM712, and EM710 and EM712, which will be operating using dual SWAT and 3 sectors per SWAT, meaning you'll see some plots such as this one, where the first row will be associated to the sectors of the first SWAT, the second row, second SWAT. And so the first step consists on obtaining a reference. And for that, I'm building upon the results that Guimarães, a former CCOM student, obtained over several reference areas. And he built upon some previous researches, such as Weber and Ward, where they used FM modulated pulses to get calibrated a backscatter at a single grazing angle, but over a broad band of frequencies. And again, he also took inspiration on Lefterakis et al., which used 2 narrow band frequencies to get calibrated backscatter, but this time over a wide range of grazing angles. So Guimarães combined these 2 approaches, and so he got calibrated backscatter observations over a wide range of grazing angles and a broad band of frequencies, allowing him to construct multispectral ARCs over several reference areas, which are this one, established in British Columbia, Canada. And let's take a look at one of these reference areas. So in here, we have the calibrated backscatter collected by Guimarães, plotted by grazing angle and frequency. And you can already see that we have some noise, especially at low grazing angles. And that's basically due to low signal to noise ratio, especially visible at higher frequencies. And we also have some noise at high grazing angles. And that's because Guimarães' technique of calculating the grazing angle associated with the bottom backscatter strength estimate was not as refined for near normal incidence geometries. So we get that noise at normal incidences. So if we slice these multispectral ARC at a specific frequency, for example, one of the frequencies that EM710 operating in very shallow mode uses for one of its sectors, we can see all that associated noise I have mentioned. To deal with that, I fit a generic seafloor acoustic backscatter model on the data, and that's my reference ARC for the frequency of that sector. And I can do that to every sector, and now, voila, I have a reference ARC for every sector of EM710 operating in very shallow mode. Then let's see how to deal with the applied gains by Kongsberg on its backscatter data. So we expect our backscatter data to be as we expected from an ARC, to have a specular peak and an angular roll-off. However, it's applied over that data time varying gain that will suppress that specular peak and flatten that angular roll-off. And that's performed because to facilitate a user in real time to better distinguish between seafloor types with different acoustic properties. But we want to reconstruct our ARC, so we have to remove the TVG, and to remove these gains, we have to reconstruct them. And these gains are made of three components: a Lambertian near normal incidence and an insonified area correction. And we can reconstruct the first two, the Lambertian and near normal incidence corrections, fairly well, because the documentation we have about this TVG is good enough for that. But regarding the insonified area correction, there are some ambiguities. And basically, we have to guess some of the options that were taken by the manufacturer. For example, what's the pulse length that they are using? We don't know for sure. Are the beam widths they use to calculate the insonified area corrected for steering and for frequency? I don't know for sure. So I have to guess. Thankfully, the new Kongsberg format, well, not so new anymore, it's out for a few years now, but KML stores the TVG that is applied to the data in the actual datagram. So it's just there. I don't have to guess anything. I can just subtract it. The next step of the technique, this technique, is to compute the grazing angle associated to every backscatter estimate. And to do so, thankfully, we have a multi-beam with bathymetric data available, so we can construct a digital terrain model after it. We can also define a beam vector, a beam direction on the seafloor associated to the sounding that's in turn associated to the backscatter estimates that we are evaluating. And we have that sounding, we can find the adjacent DTM nodes, and from those we can define a plane that will emulate the slope of the seafloor, the regional slope of the seafloor at that observation. And by having that plane and having the beam direction, we can just estimate their angle, and then we have our grazing angle estimate. Now let's see how we construct the insonified area for every estimate. Let's first consider an oblique geometry. We have our transmit beam footprint, we have our receive beam footprint, our transmit pulse projection on the seafloor. Oh, Val, please.
Sorry.
No problem.
Well, go ahead.
Just hope everybody can see it. I was just highlighting something.
It goes up, you have a good idea.
So in this case, since our transmit pulse projection is narrower than our receive beam footprint, we typically say that we have a pulse length limited insonified area. However, for geometries closer to normal incidence, we typically have the receive beam footprint narrower than the transmit pulse projection. And so we say that our insonified area is beam width limited. And in both cases, we are approximating that insonified area by a rectangle, which might not be the best, but it's a common used approach. And in both cases, we account for the grazing angle that we used in the previous step. But the TVG, Kongsberg's TVG, already provided us with an insonified area estimate. So why are we recalculating it? Well, the grazing angle that the insonified area component of the TVG uses assumes a planar seafloor. And as you all know, the seafloor, it's not flat, it's not a plane. And I told you before that to compute the grazing angle that I'm using a bathymetric DTM. So in principle, I'm accounting for the geomorphology. Furthermore, when they generate the insonified area correction, they only use data from a single SWOT. So there is no way for them to account for the seafloor's long track slope. And that's another reason for recalculate the insonified area. But when we look into into these insonified area models, so a pulse length limited and a beam width limited insonified area, and we plot them by grazing angle, we still have to choose between the two. And I kind of hinted to how it's typically done. We just choose the smallest of the two, the minimal insonified area. And that's also how I think that the dot hole, the insonified area from the dot hole format is being performed. But KML, they do this transition differently. They avoid that step transition between regimes, and they smooth out the transition. And I tested both approaches in my insonified area model, and I got better results with the smooth approach. And that's the one I'm using. Now let's take a look on how we map each backscatter estimate on a sonar referenced space. In here we have the footprint of a transmit beam, and it's being sampled by receive beams at different locations. And while the most rapid variation occurs in the along track direction, that one is integrated by inside the equivalent beam width. And so the variation that I'm really interested in characterizing will be the across track variation of the transmit beam pattern. And in here we have the receive beam pattern also projected on the seafloor, and we can also see that it's being sampled differently at different locations. In this case, according to the long track steering angle of a transmit beam, for example, accounting for pitch stabilization, or in the case of a multi-sector system to perform yaw stabilization. And again, the most rapid transition or the most rapid variation of the beam pattern is in the across track direction, but this transition will always be integrated within the transmit pulse projection, at least for the most cases. And so the variability that I'm more interested in is the along track variation of the receive beam pattern. Therefore, I map, to better understand the beam pattern variation, I map all the backscatter strength estimates in a sonar referenced space where the coordinates are the sonar referenced angle across track, the sonar referenced angle at transmission, which is basically the sonar referenced angle in the across track direction, and is measured at transmission with respect to the transmit array. And the other coordinate will be the sonar referenced angle at reception, which is basically the sonar referenced angle along track. And this was first implemented by Hiroshi in 2016, and I'm building upon his work as well by implementing this geometry. Finally, let's see how we derive the actual backscatter correctors. So first, I separate all the data by sector, and we can look into a specific sector and subdivide it by sonar referenced angle beams. And we can look into a specific beam. And when we look at that data, we can further separate it, sort it by grazing angle. And why do we have different grazing angles for a sonar referenced angle combination? Well, because we might have seafloors with different morphologies, and also our vessel might present different orientations with respect to the seafloor. So having many boats or many slopes will give us several grazing angles for the same SRA combination. To deal with that, I just select the grazing angle subbeam with most samples, and let's take a look at it. And over it, I can define my mean and calibrated backscatter, which I represented there with the vertical red dashed line, and compare it against my reference backscatter. And how do I get my reference backscatter? Well, from the first step, we defined for each sector, a reference ARC. We know in which sector we are working. We know which grazing angle we are considering. So obtaining a reference backscatter value, it's easy. And to compare those, well, I just evaluate the difference between the mean and calibrated backscatter and the reference backscatter. So we can do that for all beam in the sector, all sectors in the data set. And in the end, we get what I call a correction heat map. Again, every row, the first row it contains the sectors of the first SWOT, second row, the sectors of the second SWOT. The x-axis is our sonar referenced angle across track, and the y-axis the sonar referenced angle along track. And of course, every pixel of each plot will be the color-coded backscatter corrector that was computed. And when we slice our heat maps at a specific sonar referenced angle along track, we see on average how the correctors vary in the across track direction. And you can see that, especially for the outer sectors, we get corrections as big as 7 dBs. And of course, on the plots on the right, you can also see on average how the correctors change in an along track direction. So in these plots, I'm presenting the data, the ARCs, the uncalibrated ARCs. So before applying the correction heat map, and again, you can see for the outer sectors, for some of those at least, the 7 dB departure from the reference ARCs that we defined for each sector. And when we apply the correction heat maps, we snap our ARCs into each sector's reference. Looking into the same sort of data, but now in a mosaic format, we have the uncorrected data in here where we can see pretty well the sector boundaries. But after you apply the correction heat map, these disappear and we can recognize a nice angular roll-off. So we have looked into the process. We finished all the steps. So we can just take our correction heat maps, apply them on our multi-beam and go and calibrate the backscatter. I wish it was that easy. However, we also thought that, well, the correction heat map should be independent of our reference area. If we are using the same sonar, the same mode, if we run it over a reference area, we get one correction heat map. It should be the same as the correction heat map that we get if you use a completely different reference area. And so we tested for that. So on the left, we have the heat map that was generated with one reference area. On the right, same system, same mode, but a different reference area. And they have different seafloor types and different depths. So they should be these are totally independent data sets. And so I'll just flick between the two heat maps. And just by doing that, you can see that there are some maybe not so subtle differences. And this is actually the difference between the two. And I could lie you with statistics and just tell you, okay, I have an average difference of 1 dB and a standard deviation of less than 1 dB, and just show you that. But when we look at this plot, we see that in fact, what we have here is that the correction heat maps agree with each other, but only within plus or minus 2 dBs. And reasons for that. Well, in the outer sectors, we can spot a slight range-dependent trend, and that might have at least partially something to do with a miscalculation in our attenuation components. Also, remember, our correction heat maps will only be as good as our truths, our reference ARCs. If those have some inaccuracies, those will also be inherited by the correction heat maps and show as a departure on the difference between the heat maps. Also, we are using the dot-hole format. We don't know really well what's the TVG, the insonified area component that's being applied, and that might also be contributing to some of the departure. And on top of all of that, and sadly, in my opinion, I don't think we are handling near normal incidence geometries as well as we could. I think there is some further work to be done at those kinds of geometries. And I don't think I reached there with my arm, but that might contribute significantly to this deformation, as I call it, in our difference between heat maps. In here, we have the same train of thought, but the only thing that changes is the system we are using. This time we are comparing heat maps for an EM712. But same mode, very shallow mode, again, two different reference areas. And the main difference that we have is that this system uses the KML format. So we were expecting better results because at least we know for sure what the ensonified area component of the TVG is. Unfortunately, they don't look much better, and we can't blame on that component anymore. So there definitely might be something wrong with the way we are handling normal incidence geometries. And all the rest of the departures can be explained in the same way I explained for the previous difference map. So Guimarães established these 5 reference areas, and they are great. However, especially when considering a large research vessel, I would say that they are in shallow locations. They are in locations that are surrounded by heavy ferry and recreational traffic. And also, we have limited room for maneuvering. On top of all of that, they are in Canadian territorial waters. So if you want a national asset from another country to use those areas, you cannot do that. At least not without some a significant amount of bureaucracy. And with that in mind, last April, we spotted this transect along the Canada-US border that seemed to tick all the boxes. It was deep enough, it was away from shipping lanes, plenty of room for a large research vessel to maneuver, and on the border. So typically both, at least ships from Canada and US might be able to use it without too much paperwork. And so we took our calibrated EM712 in those reference areas from Guimarães, and we collected data along this transect. And just another side note, it could be a perfect place to calibrate a multi-beam for a ship that is transiting from the San Francisco area to Alaska, or even for ships located in the Seattle area. It will be really close to that transect. So along that transect, we identified a smaller sub-transect with significantly homogeneous and high bottom backscatter strength at a depth of around 100 meters. And we used our calibrated 712 to generate reference ARCs for that area, at least for the frequencies that are used in very shallow and shallow mode by the EM712. And they actually agree pretty well if you pretend not to see grazing angles between normal incidence and 80 degrees. And they should look the same because despite using different modes, the frequencies they use are only 11 kilohertz apart. However, at near normal incidences, we have a problem. And again, I have cited several reasons that might be making this happen, and we can have our truths might not be good enough, but on top of that, I think that we are not handling our near normal incidence geometries as well as we could, and some more work could be done to correct that. So to conclude, is the truth true? We are not sure, especially at high grazing angles, for the reasons that we showed. And there might be a questionable handling of near normal incidence geometries that might be especially affecting the way we calculate our insonified area at these geometries. However, we obtained the correction heat map. We can say with some tolerance that we are able to calibrate a multi-beam echosounder, a multi-sector, multi-SWOT, fully motion compensated multi-beam. And to do that, we built upon the work of Guimarães with his reference areas, LF Terakis et al. With his reference area calibration approach, and Hiroji with his sonar referenced angle geometry. We investigated how repeatable these correction heat maps are, and we saw that they agree within plus or minus 2 dB. And finally, we investigated how to propagate a reference area by using a calibrated system into another area that might be more suitable for other research vessels to use, at least at the frequencies that sonar uses. And before we run into questions, I'd like just to thank the Portuguese Navy for funding my 2 years of education in the US at UNH. I'd like to thank all the faculty and staff of CCOM. Some of them are here today. It was a great learning experience from all of you, and even the staff. They always helped with all the logistical needs that I had. And also Kongsberg for providing some enlightenment in how to deal with some of the quirks of their equipment. And on top of that, I'd like to thank a special word of thank you to Professor John Hughes Clark, always using the latest technology to teach his students, a broomstick for scale. And thank you for these 2 years of mentoring. And I'd also like to thank my family who supported my adventure in this academic environment. Thank you, my daughter Lara, for proofreading my dissertation. And yeah, it was great for all of us to be here, and without their support, I wouldn't be able to do this work, for sure. And that's all I had to say for today. Thank you for listening.
Thank you very much. And what we'd like to do now is go through a series of questions. We're going to start off spinning through the committee, and I've got questions from Brian, and so I'll give those, and we'll go through you guys, and I'll ask a few, and then we have the option for another loop. So I think that's the way I'd like to progress it. So what I'm going to do is ask Brian's given me a number of questions he'd like to be asked, but one of them was actually if you have a chance, maybe you could just have your thesis there, just because he refers to figures that aren't necessarily in your presentation. So just have a pause while we get that. Yeah, one of the things he made the comment on is that everything snaps beautifully to the result, but he felt that there was the trouble was you had a training data set and then you corrected the training data set, so they weren't independent. And the way you chose to compare was to just take the heat maps against each other. And what he was asking is, did you then take these are corrections, for example, from the cobbled area and apply it to the data from the shell hash area or the other three?
I didn't do that. As you said, I used the trained data set to apply the solution I got, which is biased to say the least. But when we use those correction heat maps that we compare two correction heat maps, part of the departures that we are seeing will just show you that, I think, because I'm not applying the corrections there, a correction heat map on data from another set, but I'm comparing two different data sets that are supposed to be, I'm comparing the results itself, the correction heat maps. And that should show us that if the departure is 0, this will happen, regardless of the correction heat map that I use. But we saw that we have some departures. So I know that if I used for it, this is for a shell ash reference area. So if I use the cobbles correction heat map on this data, it wouldn't snap into this reference because we have some departures. For that to happen, we would have to have a flat 0 difference between correction heat maps. And I showed that that doesn't happen.
I think one of the questions he's asking then is, even if the heat maps matched exactly, then you went to the two areas, would there be any other reason that this would not snap as well to the theoretical? Are there any operational aspects?
There could be, but that would mean there would have been some problem in the way that I obtained the data, for example, not using a good attenuation coefficient. I think that would be the main, or some problem in bottom detection. And we could be tracking a layer that it's, for example, if you use medium mode on a 20 meters from EM710, a medium mode, so very large pulse lengths, we might not be getting the correct bottom tracking and not the associated correct bottom backscatter strength estimates. And that could be a reason that it wouldn't work. But in principle, if everything is operationally performed correctly, if we have a good bottom tracking, if we have a good correction, a good attenuation coefficient, I think there is no reason for them not to match.
Okay, and the last one, there was a continuation of that same question. You had the option of subtracting these two heat maps. You never generated a heat map for the three other areas for some operational reasons you might want to comment on. But you could then, now with these heat maps, actually estimate the truth of those other three areas and compare it with the truth without going through the heat maps. Do you think there would be a benefit of having more comparisons than just one difference between two heat maps?
In hindsight, that would be a great thing to have included. But going back to the first reason why I didn't use all the areas, well, I showed you before that we had some noise, especially at the lower grazing angles because of signal to noise ratio issues, and also at high grazing angles. And so the high grazing angle issues with our reference angular response curve will actually affect our specular component. And if I have a very steep specular component in my angular response curve, and that's wrong, that will, when I apply that generic seafloor, that GSAB model on the data, I might not get a good emulation of that specular component. Knowing that, I chose the two reference areas with basically only Lambertian roll-off from in its angular response curve. So I tried to exclude areas with a steep specular peak because they will be less forgiving for the reference data set that I'm using, especially that grazing angle computation issue. I might put the peak at a different grazing angle or not even get it at all. And that's why I didn't use those. I only used the Lambertian reference areas. Thank you very much.
Okay, I think that's enough of Ryan's question. Perhaps Tom, do you want to?
Sure. Actually, I'll pick up right where you left off on the normal incidence thing. I think it'd be worth kind of digging into that a little bit, and I think there's lots of questions to ask there. But one question is, I guess, that sounds wise actually to look at the rough area, which is more Lambertian and has less of a specular or a peak associated with a near specular incidence or very high grazing. Did you explore how well that worked? Because then once you have that, actually, then you have your calibration. Presumably that works better at normal incidence. Could you recover those spectral peaks that presumably are there in some of the softer, smoother sediments? You know what I'm asking?
I think I understand. If by using a Lambertian area, I could recover the specular peak that was failing by using the split beam technique from Guimarães.
Correct.
I think that would work. I do. The problem is that currently the way that I'm handling the normal incidence geometry, and I say that because I look at that ARC that I generated from that border transect, and that the difference between when I compare for the same system and same mode, but different reference areas, and I get that difference heat map, I have some deformity there that it could exist, of course, but it doesn't make much sense, especially not reaching near normal incidence. We have a general trend that it changes completely. So I'm assuming I'm not dealing with that transition between a mostly pulse limited insonified area to a mostly beam width limited insonified area. And I'm not dealing with that computation perfectly. And if I think that if I fail something in that region, I will have a grazing angle bias, and that will affect a lot my insonified area computation, which will give birth to these results. But if I could go through, if I could get past that, I think I could use my calibration to get the angle response curve from an area with a specular peak.
Be interesting to look to see if
Yeah.
it actually could pop out of the data, because I think there's a lot of really valuable information in that transition. We stay away from it from a backscatter mosaic perspective, but from a information content perspective, there's a lot there. I think it's worth pulling it out. You're saying that you, and then I'll this, but you're saying, just on that same topic, you're saying that you're assuming it's because of an area correction. And I guess my question is, you don't really have to, you can maybe condition that assumption a little bit or explore that assumption a little bit by looking at how far you're off and then what that would mean in terms of an area correction. So you might, I think you're off by 3 or even more dB in some places in terms of that near normal incidence backscatter. That means that if it's just insonified area, then you have to be off by a factor of 2 or more there. And so is that plausible given your models? Can you be off by that much in the insonified area, or does that suggest that maybe it's something else? And I don't know the answer. I'm just wondering,
I thought about it. I could have pulled the thread further.
I didn't want to say.
but I thought of that, and I actually, for that transition that I'm using between the pulse length limited area and the beam width limited area, that smoother transition,
yeah,
I modeled, if I can say so, the bias that a 1 degree grazing angle error would result in an insonified area. And it seemed to explain it, at least partially.
Okay.
Because I think maybe I can show the picture.
So it's a trouble estimating the C4 slope. Is that what you're saying?
I actually,
grazing angle, or
but a combination of the two, actually, because I estimate the seafloor slope through that plane that I explained.
Yeah.
I get my beam vector,
yeah,
and so I never separate the slope component. Actually, the plane is the slope. So, but I would say that the problem is in somewhere in that computation. Yes, but what I was talking about. So for this problem that I have here, it doesn't take a big grazing angle error to affect the insonified area to get that bias. In fact, I think I copied. Sorry, it was the last one. So in here, I use the same pulse lengths that I'm using, and the pulse lengths are important because if we have a long pulse length, our beam width limited area will reach that region of the insonified area sooner. And when we are in the pulse length regime, when we are at near normal grazing angle, since we are dividing by the sine of the grazing angle, a small change in the grazing angle will result in a big difference of the resulting insonified area correction. But if the pulse length is larger, so we enter the beam width region of the insonified area sooner, we don't get to such a sensibility to grazing angle. And that's why we have, for a smaller pulse length, much bigger biases associated with the grazing angle error than we do for a longer pulse length. And so I think there might be an angle with problem with the grazing angle computation that could explain that near nadir dip, which is not natural unless we found a new type of sediment.
Here's that you're seeing biases that are much larger than what you're showing on the slide here. Is that true? I thought you were up to like 3 dB or something, or more. So from 10 to 3 dB, maybe it's a little bit less in some cases, but
I think that would be the main cause of it. There might be some underlying issues, such as, is our true set near normal incidence the correct value? And it all adds up, right? So, but I think the main reason would be a grazing angle bias.
okay.
Yeah, it wouldn't fully explain it, as you say. There might be something else.
Okay, and the figure on the left is actually from the.
Yeah, this is the shell ash ARC, and this is the cobbles.
But the source of that data is the EK80s.
Yes.
Which have a much larger beam width. And
7,
presumably
yeah.
less sensitive. to
5
this
degrees
issue.
to a, yeah.
Yeah.
And sorry.
No, I feel like there's it seems like there might be more to the story there.
And that's, my questions are all basically focused on the same figure, so you've covered a lot, but I was gonna ask a question in a a different question, but I think it's really, I think, might be misunderstanding, leading to the same conclusion. And the question I was going to ask is that your DTM that you use has a fundamentally different resolution than your, particularly when you're in the pulse-limited regime, than the resolution of your backscatter.
Yeah, it's true.
And that in itself,
That would contribute to a bias.
yeah, but that bias is, I think, going to be expressed exactly the way you're seeing it, that you're going to have a grazing angle and insonified area mismatch that is not truly representative unless you can actually get a DTM that's on the scale of pulse wind
The footprint, yeah.
footprint. Yeah, and so I think that when I saw that was kind of what I think these are all kind of pulling on the same thread. The other question I had, it really comes back to, I know you picked of course grain sediments, so they be Lambertian,
Yes.
but your conclusion that they're Lambertian comes from the earlier thesis work, the picture we see.
Exactly, yes.
And yet, at near nadir, what you call noise, may, as I look at it, when I saw it, I said, well, that's part of the specular component of what's going on near nadir. And so maybe it isn't really purely Lambertian, and maybe there is a specular component.
And I might be flattening when I apply that model. I thought of that as well, but digging into the actual geology and consulting with
Never trust geology or geologists.
That'll get you within about 7 or 8 weeks.
Yeah, that could be a reason, of course, because to get away from that noise, I'm limiting the range of grazing angles that I'm using to fit my model. And I'm kind of, okay, this is not validated, but it could be. But I had to take an assumption and I assumed it wasn't.
Yeah, and I'd be intrigued if you, because again, one of the curves you showed, I mean, it looked to me just like there was.
Yeah, I know what you mean.
A specular component to that you just called noise.
Slide 22. Yeah, I saw the same thing. Just had the same interpretation.
Except it's not there at 100 kilohertz.
Yeah.
Okay. All right. Well, I didn't know. Yeah.
Sorry.
Right.
Yeah.
Yeah, and so I'd be intrigued if you included that, as a specular component.
What
and
results
see
would
the
be
impact. See the impact of that.
And that's another thing, because the frequencies are not very far apart. We have between 70 and 100. And as you said, there might be a specular component that I'll be dismissing. But also, as John said, we don't see this at 100 kilohertz. But on top of that, we also have a different Lambertian roll-off regime for the one, significantly different than for the other frequencies. So that's why I also state that there might be something wrong with the references that we are using. Now, I just don't know really what it is.
So all right, it's just so intriguing. And I have to say, really, really well presented. So my other question is kind of a philosophical one. And you keep falling back to the fact that in the .all files, you have to reverse engineer, you have to figure out, I assume we've asked Kongsberg?
Yes.
And
The replies have not always been consistent, and they've told us, well, I don't think you know that, but and Tom might want to comment on this, but they've suggested that things have changed over the years. So we would have to relate it to version numbers as to what insonified area model is used.
And the original document from Eric Hammerstad, it uses not a completely different, but a different way of transitioning between insonified area regimes. For example, in that original document, the beam width limited insonified area would only be computed like that if the slant range was smaller than the minimum, not the minimum, but what they call the R naught, which is supposed to be the minimum slant range. But I didn't use that model. And why? Because I found some papers, including one from Tom and several others, that's from a certain year onward, started using the minimum insonified area approach. And then I assumed, okay, this must be the correct one. And the systems we are using I think they are the latest versions of .all, so they must have the latest trend, I would say. But I wasn't able to pinpoint in the literature, from Kongsberg at least, where that when and in which version that change happened. I heard that there might have been some meetings, but I haven't found the proceedings of that of those meetings to check when and in which version that transition occurred.
We went through an exercise a few years ago. Mike is in the room.
He's on Zoom.
Oh, he's on Zoom. So I remember Mike Smith, and I forget who else was part of that, Giuseppe for sure, going through and looking at the Hammerstead document and then looking at what we see in the data and trying to rectify those two. And at one point we had a Word document that had sort of a translation between the two. And you couldn't just go directly from the Hammerstead document, as I'm sure you guys know. But I don't think we did that as a functional version. And that would be that would take some time in archaeology or something like that with versions of software or something. That sounds like a good activity for Backscatter working group type crowd. But yeah, that's tricky. That's tricky with every manufacturer.
But KMO, on other end, they provide us with the TVG, and while that transition, we don't actually have the documentation. We were able to email Kongsberg and they replied to us, and we can actually test what they are doing because they record what they are actually applying. And so we model after what we think they are doing and we see the departures. And those were quite good. But in fact, we still found some versions with the correct TVG as they say that is applied, but then is recorded wrongly. And we were able to pinpoint those versions because we could do that comparison.
Yeah. And
also they alerted that there might be a version where the TVG is not stored correctly. And we have data for the 2040p that actually matches really well. We don't see any of those departures. I think it would not be fair to just present the good stuff. And we saw that was a mistake. It was not being applied well. And I didn't know that initially. And so we were having some departures, but then I was able to figure that out, and then the difference between correction heat maps was almost a flat zero.
And what's your thoughts about the hope of doing this sort of thing for other manufacturers?
I haven't looked into the documentation of other manufacturers, but I think the main point will be the same. To have proper documentation and store all the data that we need to recreate wherever gains are being applied by the manufacturer. I think if we have that, and if the systems, and I think they are, repeatable in what they put out into the water and what they receive, I think we will be able to do that.
This has been the mantra of the Backscatter working group. Questions on it?
Okay. I don't want to keep on going on this near native, but I think it's huge. As long as we avoid near native, things sort of be shiny, but we're kind of throwing away the diamond.
And can I just say something? In our defense, I show that departure, and well, it seems big, but if I do the standard deviation of dBs, not of the linear intensities for each sector, for those heat maps that you saw, those differences, it's even for the center sector, it's less than 1 dB. And for the outer sector, it approaches 0.5 dBs. Sorry, John.
No, it's useful to say, and of course, some of Tony Lyon's recent work is somewhat impressive as we're trying to chase down this level. He's showing that there's natural seasonal variability that is 5 or 6 dB. So it's never going to be boring. One of the things you very happily adopted the new transition between the beam width limited and pulse length limited, the Kongsberg one where they blend the two.
Yes.
Just find that figure. Oh, yeah. Is the KMO transition looks lovely, and you used it because it gave you better results, but can you think of any physical reason why? Because that's a significant step. I mean, at nadir it's the same, at normal incidence it's the same, and then it converges further out. That's worth 1.5 dB. That's all in that transition zone. did you get any feel when Shell provided you with that function that they were using as to why we should think about the area not increasing for a while and then dropping?
Well, the reason I got was they were having bad results when they started using the total pulse length I think in the .all versions. I don't have any confirmation of that, by the way, but in that email, they told me that they changed from using the total pulse length to the effective pulse length, and they started seeing some weird artifacts in their backscatter estimates. And so they decided to try this approach in the unsonified area, and they got better results. And that was the justification that was used. I not see. First of all, most of these areas, they use a rectangle as an approach. So I'm pretty sure that our insonified area won't be a rectangle, and that might justify a couple of tens of dBs in how wrong we are. But in the transition between this discontinuity that we have in the original model, that step function, I'm not sure about the physical justification for that, but it doesn't seem too natural to me as well, that we have an insonified area growing at a certain rate, and then it suddenly changes that rate abruptly. Not sure why. I think it's a good research topic. Not sure how physically that will happen. What I know is that this transition, the KMO one, is more forgiving of some grazing angles discontinuities, because we don't have that step-like transition where we can commit lots of blunders. So if by using this one, and that's, I think it justifies the better results I got with this approach.
Okay. Actually, I'll go on to.
Can I ask a question?
Yeah.
On that topic? I may interrupt your questioning, but what makes better? Like, what is better? Is it just
The correction heat maps looking closer to each other.
It's not actually in the angular response. It's in the backscatter mosaic. You don't see the step in that. Is that what?
No. When I say it's better, is because my correction heat maps the difference from the same sonar smaller.
Oh, okay.
Actually, before I know that.
Matches the EK80 better then.
Yep.
Okay.
Not only the EK80, but the whole process of reducting the backscatter. So I have to remove their insonified area estimate and I replace it with my own. So I think that by using this approach, my insonified area will be more repeatable for different, will be better for one data set, which will end up in repeatable correction heat map. So what I'm saying, I guess, is that the reduction process, it's better, it's more forgiving of such grazing angle biases, and that ends up resulting in more identical correction heat maps.
Okay, no worries. Let's go to a couple more of Brian's questions. In your thesis figure 5.8, yeah, that one, it's the simplification, the plane.
Which is wrong.
Which is wrong, actually. I think part of his question is if you'd like to tell us why it's wrong, but also one of his the second part of that question is why, he's asking why didn't they do better given that they have a cross-track topography? Do you have any feel for why they chose to use a simplification which isn't quite in that figure?
I can show the correct one.
Yeah, that's like it.
So do you say that this is wrong because it doesn't represent what Kongsberg actually does?
Yes,
or
yes.
because it doesn't represent?
What I did before, I was saying that this grazing angle was actually here. But what they do is, okay, we assume the minimum slant range and we defined, based on this orthogonal geometry, we defined a planar seafloor based on that. And so based on each two-way time travel for each sounding, what they do is they just swing this range into this assumed seafloor and provide us and use this grazing angle estimate to compute the insonified area correction. Yeah, and I don't know where my head was when I drew the previous figure, but this is the correct one, which I'll happily update in the last final version.
So his question is, please explain why Kongsberg didn't use the full cross-track topography. Obviously, we can't ask them, at the moment. I'm sure I could. But is there a reason why you would avoid using the instantaneous cross-track slopes?
Maybe because of the noise between the soundings, the bottom detection for each SWOT. Maybe you will have a very noisy resulting grazing angle estimate associated to every sounding, and that would result in a not so smooth seabed image tear off in CIS5. So we'll have a seabed image that will look certainly different, but maybe more rough, and it could be harder for the real-time user to distinguish between seafloors of different acoustic properties. I could also say that the computing power would be a bit more. It will take some more computing power, but I don't think that's the case. I don't think that's such a hard computation to perform.
And one of the other things, he was interested in you moving the calibration from one site to the other. Just operationally, I'm thinking whether it's the CHS or NOAA, they could move it, or it could be David Evans and Associates could go to a calibration site that NOAA provided, they could move it into their area. But how much do you think what loss happens if that? Could someone then take that transfer calibration site and move it again? So his question is, how often do you believe the transfer of calibration, not going back to the original EKs, but basically running a system over one and saying it's golden and going somewhere else, then someone picking up that not so golden and going somewhere else? How often do you believe, and of course that's just an opinion at this point, how many times could you do that transfer before the uncertainty would increase to a level where you're dreaming?
I can't quantify that. Yeah, I don't think I can. I will just be throwing random numbers into the air. But what you say, we start with a golden multibeam using your analogy, and we will get subsequently less golden multibeam.
Silver.
Yeah, silver, bronze. And so what I want to say is that, and as you said, the biases in our calibration will start adding up. And at some point, the ARC that we established for a certain area after transferring it 3 times or 4 times will have significant biases, especially if we keep that near normal incidence geometry problem. However, for the rest of the ARC, that would also keep adding up some uncertainty to it, but it will be a lot less. However, it wouldn't be the same as using it originally as acquired from the EK80, which also has its uncertainties, as we talked about. But with each transition, we keep adding up the error associated to this calibration process.
Tom, do you want to say something?
Sure. I feel like on that note, that if you knew the uncertainty in your process, you get just your propagation of error. The problem is, when is the error big enough that you're no longer happy with it? I'm not sure anyone even knows the answer to that. I'm not sure anyone knows the answer where you're trying to get to.
Yes,
Like,
Backscatter
how
working
much
group
uncertainty
document
is too
says
much?
about 2 dB, but you've already said
What
that.
does that mean? Yeah. Well, I mean, and why?
you
But
know,
so it becomes a philosophical thing.
No, I mean, Moscow went and took a look at all the components. And the instrument itself, you ping it for a week and it's got a dB, just the sonar. So I think that's realistic in what our expectations.
Depends on your goal, I guess, too, right? But related to that is an actual question, which is on your very first or second slide today, you had the different kind of things that you were thinking about. One, which was the physical characteristics of the seafloor, but you didn't include the biological characteristics of the seafloor and changes in fauna or patchiness of fauna.
Even the overlaying oceanography,
Exactly, the overlaying oceanography as well, which might say when you want to go do this. All of those could. And it could also say where you would want to go. Can you talk about that a little bit in terms of someone that says this is great, which it is. I'd like to go make a reference surface. Here's where I live, and I'd like to make it near me. What should I look for, and when should I try to go there? how often do I have to, what are the factors I have to worry about in terms of recalibrating my reference surface?
Oh, I think the broader question is what makes a good reference area?
Sure.
And in my opinion, it will be a place that's in a perfect world, you measure once and it's stable forever. And that will mean that, and of course, stable in every direction as well. So it will be a place without any azimuth dependence. So no small sand ripples occurring and changing directions between seasons, for example. That will be a plus. The thing that you addressed before, for example, not having in the summer life growing in our seafloor, that will change our scattering. And also oceanographic components that do not change a lot, because the backscatter that we get, some of it will be influenced by the acoustic impedance in the interface and that will depend on the temperature and density of the overlaying water. So we don't also want that to change a lot, because even if it's a small factor, it's something that also contributes. So basically, we want something that doesn't exist, I guess. We wanted the perfect place. But since that doesn't exist, what I think it will be the best approach is to look into the surrounding geology. For example, the places that we used have fast currents and so don't allow for sediment deposition, a lot of sediment deposition. So in principle, the seafloor won't change as much. Before establishing the reference area, we'll also have to surveil it on a periodical basis to see if there was any seasonal change. And if there wasn't, that would be a great place to establish it. And by change, I mean the biology, but also what are the structures that occur on the seafloor that might produce azimuth dependence on the data that we get. And something that we addressed as well, and accounting for all these problems, a rough surface as well would be the best, because then we avoid the specular components, because that gave us some problems, as we saw. And and then there are the anthropologic issues as well. We don't want an area that's always being occupied by fishermen or by recreational boats or ferries crossing the area, because then we wouldn't be able to navigate in there. Furthermore, we also want a big enough area, big and homogeneous, so that we can properly maneuver in there and collect our data when we are doing this reference area calibration approach. And I think that's mostly it.
You think you'll get an opportunity to go find such a site in Portugal?
I look for it. We have something called, the literal translation is technological free zones, which are areas that are dedicated for including the academic community, for scientific experimentation. And I think if we find within those areas something that is geologically and oceanographically suitable, meaning homogeneous backscatter and trying not to have azimuth dependence, I'll definitely try to establish some reference areas if I can get a hold on some split beam echosounders to do
I
so.
go to a radioactive dump site that a gravel cap has been put out, so it's toxic, nothing to live there. The gravel is, you want a nice coarse gravel.
Sounds like the perfect place.
Yeah.
Nothing else there, or is it just more eyes on people?
No, that's cool.
All right,
No, I'm okay.
I just finished with a comment. So we have Ivan's thesis, which needs some tuning on the ripples in the calibration. We have your thesis, which needs some tuning on the sonified areas near normal incidence. What should the next student be doing, given that we have a task 3 to get closer to, I'm never going to promise it, but to get closer to calibrating multi-beam backscatter? Where do you think the next thesis should be directed?
I think you kind of hinted to that, understanding how steady a reference area is. Okay, we establish a reference area, And I think there is an ongoing project over that by having a split beam echosounder pointed at the seafloor, leaving it there for a long period of time. And if we have these auxiliary sensors to understand how the conditions change, and if there is some associated change with the backscatter, I think that's probably not a mandatory step, but a reasonably interesting step to take to understand in what conditions would our reference area, what conditions would make our reference area change its bottom backscatter strength signature.
There. Yeah, there you go. No pressure. I think at this point then we've spun through twice. We'd like to open it up to the audience here. Any questions you'd like to address to Miguel?
Just a really quick question on, you listed the criteria outside of Camelot, there aren't any spots like that, but could you rank those and eliminate, and which ones, you don't have to answer that now, but narrow down the criteria?
For a reference area, you mean?
Yeah.
I would say the most important criteria would be to find an homogeneous and isotropic seafloor. And the second criteria would have to be a rough surface with no specular peak. And the third one, I would say it will be to be stable over time.
What about the anoxic?
I'm not sure what consequences would happen to the backscatter. Yes, but to the backscatter itself, I don't think there will be any consequence. No. But that would mean it would not be a good fishing ground, for example. So that would get rid of some of the traffic, and especially the fishing equipment that might do some structure, that might troll on the seafloor. So we wouldn't have to deal with that, at least I think, if there is no life over there.
But you wouldn't have any of those issues to be dead zone basically.
So apart from all the terrifying things from saying dead zone, I think it would be a good place as long as we have an homogeneous and isotropic backscatter.
I think the issue with anoxic areas is they tend to have very, very fine grained sediment. Yeah, it's really nice.
Okay, so we wouldn't get we will get a specular return. Yeah.
My favorite word that I ever learned from Larry Ward is thalweg. Right in the here locally, right
in the middle,
in the right in the center of the channel, which all swept out. It's all gravel arch bottom. Might be it.
As an MVP fishing. Yeah, whoops. I was interested.
John.
Sorry, Juliet.
So, given that backscatter changes, the biomass that changes, how valuable it would be just to have the geometry of your calibration sites stay the same over time, especially if it was broad geometry, like you had a wreck or something that was the same every time. Because a lot of what we're trying to figure out here is that angle of incidence. If you could have that as stable, would that be a valuable step to trying to figure out remaining issues?
I don't think it will be that important, because whenever we run with our multi-beam echosounder, taking into account the sediment won't change, we are collecting the geomorphology of the seafloor, so we get that update every time. And unless there will be some structure that would be created and result in an azimuth dependence, I don't think what.
If you had that azimuth dependence, would that change what you think? Like, would you be able to, with your spectral curve and spinning things, would that be a valuable thing? If you could design the ultimate spot to run over, like.
I don't think so, to be honest, because we have to always find the geometric components for us to calculate, to compute something, and it's very hard to run the same it's impossible actually to run this exact same line twice, and so we'll be updating that every time we do the calibration, because we are getting bathymetry every time we do it, and I guess that will be enough to ensure this project, even with azimuth dependency. The thing with azimuth dependency, if it was a reference area that I thought it would have some azimuth dependency, but for some reason I had to have that reference area over there, I would do just something like a star pattern. I would do several approaches, and I would see which direction would reduce the azimuth dependence effect. And so I guess I could use those lines to perform this.
So for the Kongsberg curve for calculating this sonification, as you said, there's no apparent reason for why they use that. It's just something that they thought worked better. Have you given any thought to, you said it affected your heat map, so affected the big heat map difference of parametrizing that curve between the Kongsberg curve and or whatever ideal step minimum sonification and stuff, varying that and kind of using your heat map to find an ideal curve or a better curve. I know it's kind of using
The inverts to get the model.
It might be some insight on how better calculate that sonified area.
Meaning,
Especially if it's repeatable in other areas.
meaning to tune things up to get a zero difference in my between heat maps and see what will be the area. I haven't tried to do that, but there might be some other factors that would smear that result from that inversion. But I guess it could be a valid approach. I think another interesting approach to address that would be to have a system and deploy it from different depths, getting a backscatter estimate from different depths. The backscatter shouldn't change because of the depth of the system, but what will change with the depth of the system will be the insonified area. So we would have to get those we would have to calculate those for each case very well, so we could reduce them and get the same backscatter. I guess that will be a more clean approach with less factors that would smear the eventual result.
Or pulse length, as you suggested before.
Yeah, we actually have that. We've gone through 4 different pulse lengths. We should, if they don't all agree, then we're doing something wrong.
Yep, that will have the same effect. Changing.
Pal first, yeah.
I'm not sure I'm thinking about this right. But Tom pointed out that to get a 3 dB difference in the backscatter at nadir, you have to have twice the amount of the sonified area, and or half, if you will, if I understood what you said right. And in the plots that you showed of the effect of grazing angle on that, you were talking about like 1 or 2 degrees of change or of error in the grazing angle, but I don't see how that could possibly give you, if this was the insonified area, if I tilt that by just a degree or 2, it would never change the projected portion of that area.
It will
by
change
a factor of 2, I can't imagine. And so I'm not sure that I'm thinking about it correctly. And I guess my question is, if that's right, if it doesn't change it by a factor of 2, and this is the beam limited case, then is maybe the boundary that we conventionally use for the beam of 3 dB as not the right boundary to use when you have really high signal to noise?
Let me just try to decompose that. So in the approach that I'm using for the insonified area, I don't truly have a beam width limited regime and a pulse length limited regime. I have a transition between the two. I would only truly apply the beam width limited equations at true normal incidence. And when you account for the pulse length limited area, you have, especially for high grazing angles, you are extremely sensitive to the grazing angle. And so that will change your insonified area considerably. And I think the second part would be if our 3 dB beam width would be the right beam width to use. Was that it?
Yeah.
To be honest, I don't know how to answer that. What we should use actually, it will be the equivalent beam width. What's the size of a beam width that contains with no nulls, all the energy that is projected into the seafloor, and the minus 3 dB beam width is a convenient approximation of that. But then again, it's not the equivalent beam width, and I'm not sure how different they would be, but there must be some contribution. Yes, not sure just how different that would be.
Okay, thanks.
So beating that near nadir force again. To the reference data from Ivan, you were thinking the near data was noisy because of a geometric issue. Is this the same footprint thing, or what do you think is the geometry that's
No.
going wrong?
It's a different thing, because Ivan, what he uses is he adds an oblique incidence geometry. He can get within a beam, he can get the across track profile of the seafloor. He can get several, he can finally distinguish the grazing angle at oblique incidence geometries. And that's near normal incidence. He is only able to get like an amplitude detection of the seafloor. And so what he uses to estimate the grazing angle is basically the readings that he has from the MRU that is attached to the whole rig. So he uses a function that contains the pitch and roll that is involved in the mechanical steering of the whole equipment.
So it's like a weakness in the system, essentially, that you're using.
Or in the approach, at least.
Yeah.
Because you cannot get a phase detection at near normal incidence.
You're getting the answer to your question about what should the next graduate student do.
I was thinking it's dealing with 90 to 85 degrees. It is critical. And all these equivalent beam widths and equivalent pulse length are affected, especially when you start having a little bit of 4R pitching. It's nothing like the rectangles we're dealing with. I'm not sure. Yeah, it'd be nice to have a student work on that. I think for many applications, because what you'll find is so much of the literature has got refinements on that same twisted rectangle, the transition. It's convenient, it works well enough, but in our case, it's failing. And I think a lot of it's got to do with your changing depth. If you stay within the same depth range, you get away with it because you reduce the data with that, it comes out. But as soon as you try and go to an area, which you did, you went out to 100 meters from 28 meters, and things aren't scaling correctly.
Or when I use different pulse lengths.
Yeah.
So
Again, I'll come back to Marshall, who looked at all these relationships and the changing depth and the changing pulse length, which he modeled the impact of that on the error that would create, pretty huge. And it's always around the meter area.
And we just mustn't change the depth. Or we should fly AUVs at constant altitude everywhere. Problem solved.
That's like the Landsat of us, right?
Is it so high? Yeah.
Always at this angle.
Yeah.
Never change that either.
Otherwise, I think thank you very much.